Hi, I'm Nicole.
Hi, I'm Harsh.
We're presenting S4D, Self-Taught Semi-Self Speculative Decoding, a new state-of-the-art method for hierarchical speculative decoding. TLDR, we built the first learned router via RL for hierarchical speculative decoding. We made three main contributions. First, a learned per token gate, a tiny network that decides token by token how much compute to spend. Second, a reward that balances output quality against cost. And third, a per token RL setup that actually trains it well. And the payoff, which I'll keep coming back to, we match lossless speculative decoding accuracy 0.91 at 4 times fewer expensive model calls. We Pareto dominate via SD, the previous state-of-the-art hierarchical speculative decoding method, at roughly twice its speedup and over twice its accuracy. And if we push for speed, we go up to 3.5 times faster than vanilla speculative decoding. Let's unpack it.
Generating tokens from the big model is memory bandwidth bound. It's sequential and the dominant cost of large language inference, and speculative decoding is the natural fix, where a small cheap model guesses the next few tokens, and then a big model checks all those guesses efficiently in a single forward pass. However, the one thing that controls this whole efficiency is the acceptance rate. With every wrong guess, you force a full expensive step. Now, vanilla speculative decoding is all or nothing. You either accept the small model's guess or you reject it and pay full price for the big model entirely. Via SD's insight is to add a middle option, the same big verifier model with about 45% of its layers skipped, and it's cheaper than the full model but still smarter than the drafter. But it raises the question, how do we decide which of the three tiers to use?
Via SD makes a three-way decision with two numbers picked entirely by hand, and they're simply suboptimal. When we swept all 9 threshold configurations, accuracy capped at 50%. Deciding how much compute to spend on each token based on that token's context is a textbook sequential decision problem. Our first contribution is the learn gate. We frame routing as a Markov decision process. The state for each token is a handful of cheap features, how confident the drafter and the slim model are, whether they agree, how far apart the distributions are, and where we are in the block. The action is which of the 3 tiers to use, and the policy is a tiny MDP. At inference time, the gate makes its decision instantly from cheap signals without running the expensive model just to decide.
Contribution 2 is a reward, and this is where we pull from the write-up directly. There are 2 ingredients per token, quality and also the match term. The cost is the per action latency, the drafter step, plus the slim model amortized over the block, plus the full model. But only if we escalate all normalized by the cost of 1 full model step. The reward is just match minus lambda times cost, where lambda is the knob that trades accuracy for speed.
And now contribution 3, how we actually optimize the gate. All 3 methods share the same skeleton, a policy gradient. In words, increase the probability of actions that did better on a baseline and add an entropy bonus so it keeps exploring. We use reinforce that takes 1 reward for the whole sequence, subtract a running average, and apply it to every decision. We also try GRPO where we run several rollouts of the same prompt and score each against the group. It also adds PPO clipping and a KL leash to the starting policy for stability. Our per token version gives every single decision its own advantage. Because routing is fundamentally a local choice, this is the lowest variance signal and it trains best. The one-line lesson, credit assignment, is the whole game here.
Quick proof that the training works, all 3 methods converge, reward climbs, and the rejection rate falls. This is the evidence for the credit assignment claim we just made on the last slide.
The top 2 are references, greedy decoding and lossless speculative decoding. They should be identical because speculative decoding is exact. The tiny gap we assume is just BF16 numerical noise flipping a couple of borderline problems. And now the red rows, the hand-tuned thresholds, which is the previous state-of-the-art method via SD at 0.34 and 0.40. We find that these are very low because a single global cutoff cannot separate confident and correct from confident but wrong, so it waves through a stream of locally possible but globally wrong tokens. And on GSM-AK, the final answer is all or nothing. That's why also a full 9 config sweep still caps at 0.5. There's no single cutoff that is right in every context. The imitation-only baseline is a little bit worse at 0.34 because imitation learning adds exposure bias. However, the blue rows fix exactly this. RL trains on the policy's own rollouts, which kills the exposure bias, and the match reward teaches the gate to escalate precisely on the tokens where the drafter would error. Reinforced plus MR recovers full accuracy, 0.907, matching lossless, and GRPO drives the expensive call count to the floor, 0.16 per token. And the per token version trades accuracy down to 0.71 because its per token cost penalty makes it very accept heavy. So it falls into the same over accept failure as the thresholds, just milder and far cheaper.
Same story as latency. Greedy is the 1 times baseline, and the learned gate is the fastest of all the routing methods. This one plot is the whole story though. Accuracy on the vertical axis, speed on the horizontal. The hand-tuned methods are slow and accurate, and they're completely dominated by both axes. One mechanism of fixed cutoff is forced to do 2 jobs it can't do together. It overescalates routine tokens, which makes it slow. However, dial it towards accuracy and around 0.80 or towards speed, and you get 10 times fewer expensive calls. Even better, look at the 3B drafter point. A stronger drafter hits the same 0.8 accuracy with 36 times fewer full model calls. That tells us the right lever is a better drafter, and this approach only gets stronger as the drafters improve. Bottom line, we Pareto dominate the hand-tuned baseline everywhere on this plot, which makes S4D the state of the art in hierarchical speculative decoding.
So why does this matter? First, we match lossless accuracy at 4 times fewer expensive model calls. That's a 2.2 times speed up with 0 accuracy lost. Second, it's a tunable frontier. We can make it 2.7 times faster for only a 1/10 of a point of accuracy loss, or 3.5 times faster for about 0.19, up to 10 times fewer expensive calls. And again, we Pareto dominate via SD at roughly twice its speed up and 3/10 to half a point higher accuracy.
To wrap up, we took via SD's brittle hand-tuned thresholds and turned them into a learned policy. The result? A Pareto improvement, lossless quality at a fraction of the cost, dominating the baseline, free to deploy, and getting better as models improved.